Dear students, good morning to one and all. Dear students, in the last part of the video, we have discussed about some basic terms in the nuclear magnetic resonance spectroscopy. We have also discussed about some concept related with the nuclear magnetic resonance spectroscopy. Particularly, we discussed about the different rules which are used to determine the spin of a given nuclei in terms of spin quantum number, which is a basic required condition for the molecules or for the nuclei to show the NMR spectroscopy. Dear friends, in the last part of the video, we have gone through a various concepts like about we have discussed about the motion of precessing nuclei. Dear friends, today in this part of the video, we are going to talk about the relaxation process shown by means of an spinning nuclei, how it transfers its excess energy in the surrounding. That process is known as the relaxation process. So this relaxation process is very important, which is also called as the nuclear relaxation process in the field of NMR spectroscopy. So this is simply the mechanism by which nuclear in the higher energy state, means the excited nucleus, transfer its excess energy to its surrounding, and then it returns to its ground state or the lower energy state, and this process is known as the relaxation process. And there are different ways by which it transfer or it lose its energy in the surrounding, and the first method or the mechanism by which it lose the energy is known as the spin relaxation process. So when this process or in this mechanism, the two precessing nuclei come close to one another, and the nucleus in the higher energy state, means the excited state nucleus, transfer its excess energy in the neighboring nuclei, and this mutual exchange of spin give rise to spin relaxation. So this is very important method or the mechanism by which the energy of one excited state nuclei transfer to the others precessing nuclei in the spinning state, and it results into the broadening of the line in the spectra, because the width of the spectral line is inversely proportional to the average time of nucleus spent in the excited state. The second mechanism by which it transfers its energy in the surrounding is known as the spin lattice relaxation. In this, nucleus in the higher energy state, means the excited state nucleus, transfer its energy to the other nuclei in its surrounding framework, in its environment, or which is also called lattice, and this is responsible to return the nucleus in the lower energy state, and the time taken for this transition is called as the spin lattice relaxation time. Spin lattice relaxation time, and this process is responsible to maintain the more nuclei in the lower energy state than in higher energy state, and this is the required condition for the NMR spectra. Dear friends, again the question arises, which nuclei show the NMR spectra? And the basic condition for the any nuclei to show the NMR spectra is that the nucleus must have the spin quantum number greater than 0. So I should be greater than 0, spin quantum number should be greater than 0. And the NMR spectra involving the protons are going to that we are going to be considered here. So we will talk about the NMR spectra of the proton here, and the spectra of NMR, that the NMR spectra of other nuclei are also observed to be similar to that of the proton, and that's why the NMR spectra of proton are also called as the proton magnetic resonance spectra, or simply it is known as the PMR spectra. In the NMR spectroscopy, there are different ways which are responsible to observe, or which are responsible to appear the peak of particular proton in the molecular framework, and that effect, that mechanisms are called as the shielding and the de-shielding of that proton. Actually, The isolated proton comes to resonance at a definite frequency, at a fixed frequency, at a particular frequency, and if the given sample contains the number of protons which have the same environment, actually which may or may not have the same environment, that depends upon the structure of the that particular molecule. But if all the protons in the molecule have the same environment, then the protons will resonate at the same frequency, and definitely it will give rise to a single peak. So the number of peaks indicate the different types of the proton, or the types of the proton which are present in the molecule. And this, if all the protons are having the same environment, it means that these are chemically magnetically equal or the identical, then this type of the molecule will give a single peak in the NMR spectra. And this happens with the molecule known as the tetramethylsilane. So in the TMS, tetramethylsilane, all the protons are magnetically equivalent, and hence it gives rise to a single peak. So this is the structure of tetramethylsilane. Here all protons are attached to the definitely silicon through the carbon. That's why this is the exactly identical, or that is nothing, we can say the similar environment for all the protons, tetramethylsilane. So but this is not observed all the time in case of all the molecules, and in most of the molecules the protons have different environment, and the protons therefore come to resonance at different frequencies or at different applied value of magnetic field. And this is because the electrons surrounding a proton, or this is because the proton is surrounded by means of electrons, and these electrons are responsible to generate an induced magnetic field, and which is proportional but opposite in the direction of applied magnetic field. So this induced magnetic field, because of the protons, because of the electrons surrounding the proton, this is opposite, or this is opposing the applied magnetic field, and this phenomenon is known as, or is called as, the diamagnetic shielding. And here it shields the nucleus to some extent from the effect of the applied magnetic field. Therefore the degree of electronic shielding of a proton depends on the electron density around that proton. If the electron density around that proton is greater, there will be the more shielding. So here, hence the electron density around the proton is higher, then shielding will be greater. Therefore the effective magnetic field on proton can be expressed in terms of this equation, that is H effective is equal to the difference between applied magnetic field and the induced magnetic field, and the strength of the induced magnetic field depends upon the applied field and the shielding provided by the surrounding electrons. So therefore the strength of the induced magnetic field delta into the strength of applied magnetic field. So here this delta is called as the shielding constant, and if we put this equation 2 in the equation 1, then we will get this equation, that is effective magnetic field is equal to the applied magnetic field into 1 minus delta. So proton with different environment will come to resonance at different applied field, and here if the greater is the shielding of a proton, less will be the effective field for a given applied field. Therefore here this resonance peak will appear at the lower value of field, and here it can be explained with the help of example of the halogen. You know very well, this is the order of electronegativity of different halogens, that fluorine is having the greatest electronegativity as compared to the chlorine, bromine and the iodine. Therefore consequently shielding parameters will be in the order for the methyl halides, that so in this case, so here this fluorine will attract more electron density towards itself from the CH3 group, and therefore if we compare the fluorine and the iodine, so iodine will have the lower, less electronegativity. Therefore this shielding constant for the protons in methyl iodide will be greater than the protons in the methyl fluoride. Therefore methyl protons of CH3F will come to resonance at lower applied magnetic field than the protons of other methyl halides. And this value, at what value they will come to resonance, this is given by the another well-known term known as the chemical shift. Dear friends, in the last part of the video We already discussed about too much regarding with the gyromagnetic ratio given by means of this gamma, and this gyromagnetic equation for the gyromagnetic ratio gamma is given by the equation 2 pi mu divided by h0. H0 is the applied magnetic field, mu is the frequency, and from this equation we can write the equation for this frequency gamma into strength of the applied magnetic field divided by 2 pi. So this difference between the resonance frequency of a given nucleus in different structural environment is known as the chemical shift, and here it is defined in this way. It is defined as the change in the position of resonance peak from that of the some arbitrarily chosen standard or reference molecule, and it is always denoted by the delta. So the most commonly used reference molecule in the NMR spectra is known as tetramethylsilane, with which the delta values of all remaining protons or the all other protons of the other molecules are compared. And this tetramethylsilane having a protons which are magnetically equivalent, and that's why it gives rise to sharp a single peak at the high applied magnetic field. So here these protons in the tetramethylsilane, these are not shielded, these are the highly de-shielded, and that's why it gives to single peak at the high value of applied magnetic field beyond these protons in most organic compound. The chemical shift is quantitatively expressed that the applied magnetic field of reference divided by the magnetic field of sample divided by the applied magnetic field of reference into 10 raised to 6 ppm. It can be also expressed in terms of frequency, that is the frequency for the sample minus frequency of the reference divided by frequency of reference into 10 raised to 6 ppm. And when tetramethylsilane is used as the reference, then the chemical shifts are termed as the tau, or these are reported in terms of tau, and this is given by the equation tau is equal to 10 minus delta. And for the tetramethylsilane, the chemical shift is found to be 0 because these are highly shielded protons. These are highly shielded protons, and therefore tau for this will be 10. So this tetramethylsilane is convenient to use it as a reference. Why this is so? Because of because it has some important characteristic or this important features. First is that it has 12 equivalent protons, and all the 12 protons of tetramethylsilane are having same environment, and hence it gives a single intense peak in the NMR spectra. Again, it has low boiling point 27 degrees Celsius, so it can be available in the liquid state at the room temperature. So samples can be recovered by evaporation of tetramethylsilane after the spectrum is recorded. So definitely at the room temperature, its boiling point is 27 degrees, so it will be easily evaporated, so sample can be recovered very easily. Again, it is non-reactive, means it is chemically inert towards the other substance. Again, it is miscible with almost all organic substances. That's why it's very easy to prepare the sample, and it does not take part in the intermolecular association with the sample with the other molecules of the sample. Again, tetramethylsilane shows NMR signal at very high magnetic field as compared to the low other protons, because protons in the CH3 of tetramethylsilane are highly shielded by their electrons from the external magnetic field, and hence the signal for the TMS tetramethylsilane appears at the extreme right. It means upfield of the spectrum having the delta value 0. So here the conclusion can be drawn here. If greater is the shielding, if greater is the de-shielding of proton, larger will be the value of delta. It means that if greater is the de-shielding, larger will be the delta, and if greater is the shielding, smaller will be the delta. So here this arrow indicates more de-shielding, means low field, the high frequency delta value will be greater, around 10. And this arrow indicates there is more shielding, means upfield where proton appears at the low frequency, and nearly delta value will be nearly equal to 0. So this is all about the chemical shift and the relaxation process of nucleus that we discussed in this part. Dear friends, in the next part of the video can get the information of the about the structure of the molecule based upon the position of peaks given by the different protons of the molecules. Thank you very much.